Okay, then I think we could probably start. Um, I am happy to see so many people here. It makes me anxious. But, today, finally, after months of work, after thousands of pages read, after all the papers and meetings and dozens of pages written in 3 iterations, we are happy to present the new subspace consensus. Woohoo! I hope it will make sense to you. If it doesn't, we'll have plenty of time to questions later. And I mean, if some questions come to you after the meeting, you can always feel free to ask them in the research channel or message me, and I will try to clarify them in the writings for the future. So let me share. Share, we close this. Okay, so you should see my screen with, oh yeah, there it is. So this was image generated by AI to represent the new proposed working code name of the new consensus called Dilithium proposed by Jeremiah. Maybe in the end we can vote if it's a correct name. But we hope this will power our warp engines for the subspace continuum from here on and only get better and better. So the protocol itself, it still awaits the formal security audit. We are still polishing up the details. Some details may change. The exact numerical parameters may change following benchmarks or implementation. But we do firmly believe that this is finally it, and this is finally correct. And so it's a lot of dense information. It's a lot of math. So don't worry if it's overwhelming. I tried my best to distill it to be assured as clear as possible, but forgive me if it's not. Okay, then first and foremost, we have to establish what we're going to be talking about. And it's going to be first introduction of what it is, what we mean by subspace consensus, and then the specific phases that we're going to be going through. It's going to be archiving, plotting, farming, and extraction, and some bonus slides in the end for those who really want to dig into the mess. We have to establish first and foremost the terms. And so for subspace, we define our consensus protocol as proof of archival storage. This is what been true for the previous consensus, and it is still true that we stick with. The proof of archival storage for subspace is a Nakamoto consensus protocol or longest chain protocol. It employs a proof of capacity puzzle for space-bound Sybil resistance, where by space we mean some useful storage as in proof of replication, and by the specific data that is being replicated is the archival history of the blockchain, which is supposed to be solving the farmer's dilemma that everybody has heard a lot, but we'll not be stopping on that exactly. So in the simplest form, the consensus of proof archival storage of subspace is what you can see on this diagram. It's a three-phase continuous protocol of these three phases coming from one through another, so it's hard to establish which one exactly comes first. But I'll be talking them in order of archiving phase, which is the given new blocks on the chain, construct a canonical history, same for everyone from the chain. Next phase is plotting phase, which is given the canonical history that was created during archiving, generate the unique replica, which we call the plot, and store it on disk. The third phase, once the plotting phase is done, is called consensus phase, which is given the replicas and given a challenge from a secure randomness beacon, audit the plots, that is the replicas, for a solution that satisfies some predefined threshold, And if you find some, return a proof, propose a block. And so it goes, so on and so on in the route. For the last phase, I prefer to usually interchangeably refer to it as farming phase or audit phase, because consensus may be ambiguous, since we're calling all of this consensus. So I will be calling them archiving, plotting, and farming. So for the protocol to be fair, for the block lottery to be fair, and for the history to be uniformly replicated, we want farmers to store as many probably different pieces of history as possible. The more pieces the farmer has, then the greater are their chances of proposing a new block. And to ensure that farmers store as many different pieces as possible, we enforce sampling algorithms that tells farmers which are the exact pieces of history each one of them has to store and eventually provide to the network when asked. So all of this that I've described up to this point is true for the subspace consensus was before. So the question is, why did we have to move from what we had before to the new version? What exactly is new? So the short answer to this question is to enhance security and to improve user experience. Now, there has been a lot of improvements in these two areas, and I have roughly divided them in this slide by the phase, though some of them do influence all of the phases together and the algorithm in general. This is not an exhaustive list. These are just the crown jewels. So in the archiving, the Merkle trees have been replaced with KZG commitment scheme. So the commitments are now succinct. So they are much, much smaller than they were, even for the data that is arbitrarily large. KZG also allows us to prove that the erasure coding was done correctly and the data is indeed recoverable, something that we did not have before, which we wanted to have but did not yet. The sizes of pieces in history have been significantly increased. So the amount of network requests to recover data has been reduced, which is more of user experience upgrade. The farmer plots in the plotting phase are now provably incompressible because it is information theoretically difficult to substantially compress the data that is random, or at least statistically close to random. We have removed the binary search trees that were used in consensus V1 for looking up pieces on the plot, which were the root cause of why plots in V1 consensus were much easier to compress. So that's not an issue anymore, just great development. The most second important feature that was improved in plotting is that we have changed the encoding scheme from being time-bound to, or computation-bound as the sloss algorithm, to memory-bound, or memory bandwidth-bound. So it's better resistant to ASICs. And we are actually going to be using the ideas from Chia, but I will be explaining how later. Not exactly as Chia does. So we're not just copying Chia and giving it a new name. In farming, proofs of winning blocks and winning solutions are now much shorter and they are efficiently verifiable, which is essential to our future scalability, though we do not have that problem yet. We want to be future-proof. The plot audits are now SSD friendly because we are now favoring more of random read approach from disk versus the large sequential reads. And so it's now more friendly to smaller home farms for personal computers rather than big whale hard disk farms. I will be going through these 3 stages one by one in detail. And So let's first start with archiving. So to define it precisely, archiving is a process of transforming blocks at a configured depth from the tip of the chain, when we can call the blocks confirm that they will not be reorganized, and we have that set at 100 blocks. So archiving starts at a confirmed depth from the tip of the chain, and it results in a canonical history that is ready to be distributed to farmers. The result of archiving process are segments, or archived segments as I may call them, that consist of pieces. Piece is one of the units of measurements of data in Subspace that will be mentioned frequently. And a piece consists of a record, which is the source, the actual source data coming from the chain, a short commitment to the record data, and a short witness that the data actually belongs to the history. Each record is around 32,000 chunks, well, precisely due to the power of 15 minus 1, probably. Each chunk is precisely 254 bits, uh, or around 32 bytes. Sometimes we may pad them up to be nicely divisible into 32 bytes. And a chunk is the smallest conceptual unit of measurement of data. We will be using chunks a lot because it is a field element for KZG scheme, and a lot of operations, well, maybe most of the operations, are performed exactly over chunks. Doing mathematical field operations in archiving, plotting, farming, and extraction, well, they're everywhere. In the diagram below, you can see what the piece consists of. And so the piece size in the new version is now, we're looking at 1 megabyte, but this may change following benchmarks if it proves to be too big or too small. But right now we're looking at 1 megabyte. So if it's 1 megabyte, it's going to consist from around 32,000 chunks. Each of are around 32 bytes, plus a KZG commitment, which is really short, 48 bytes, and a KZG witness, which is really short as well. So this overhead of commitment and witness versus record data is less than 5 or 0.5%. 0.5%. The main pillars under their new archiving protocol are the KZG commitments, of course, and erasure coding by polynomial oversampling. The synergy between these two things is what allows us to have succinct commitments to the data of arbitrary size, succinct witnesses of inclusion that are efficiently verifiable, and that allow us to prove correct erasure coding. KZG commitment is a primitive that is used extensively in our protocol. They're also known as KT commitments. I will not going to be stopping on this in a lot of detail. There is a wonderful primer written by Ozgun that is in our Notion and also posted on Medium. There is another one by Jeremiah and myself, so I will just iterate the main points. If you're curious, you can go read those later. So we split our data into the 254-bit chunks, as I mentioned, and this vector of chunks is uniquely represented as a set of xy coordinate points on a polynomial. What we mean by xy coordinate points, the x coordinate is just the index of the chunk sequentially in the piece, and the y is the byte value of the chunk converted to an integer. So you can represent any vector of data basically like that, and that's what we're going to be doing. Then we're going to use an interpolation to express a polynomial over this data. Now this diagram is as if it was in real numbers, but it's actually happening in the finite field, so it doesn't look like that. But you can imagine it like this. So we're going to be expressing a polynomial that's passing through our data points. Once we have that polynomial, the erasure coding process is actually going to be just, we'll take that polynomial and evaluate it on more points. The secret is when you have enough points, you can recover the polynomial from any combination of those, be it source, the extended points, some source, some extended. That works wonders for our protocol. So if in this diagram and in our use, the source data is indexes 0 to 127, then the extended data is just twice as many points. A KZG commitment, given this polynomial and the source data, is just an evaluation of the polynomial at some point values from a public trusted setup. And the KZG witness proves that this polynomial has some specific value at some specific point with respect to the commitment that we just computed. So the commitment and the witnesses are possible to compute only if the prover knows the whole polynomial or equivalently the whole source data, but they are very easy to verify by anyone. Moreover, they have constant size, as I just said, 48 bytes for any data size, which makes them very attractive and has played a lot into KZG adoption in the industry. So Ethereum is going to be using them in dark sharding. Polygon is using them for data availability. There are other protocols that are using them for zero knowledge. So they are now becoming a golden standard in the industry. So now we're going to be using them as well. There are a lot of perks to them. One of the greatest perks to KZG is the way they interoperate with erasure coding. When the erasure coding is essential for our proof of replication, because we want to be really sure that we can retrieve the data eventually. So the construction that we end up using is primarily based on paper information dispersal with provable retrievability for rollups. And one of the, or even two authors of this paper has actually helped us with this construction. So the key idea is that instead of viewing the data as just a flat byte array, as in the example on the previous slide, we are doing what we call the 1.5 dimensional approach. We're putting the data into a grid, and that proves to be surprisingly robust. So combining the polynomial nature of erasure coding and KZG with other properties of KZG can guarantee us consistency, retrievability, and the efficient variability of underlying data. So we currently archive segments of 128 records of history data, which we stack one upon another into a grid. So you can imagine each record is going to be a byte array and is going to be a row of this grid. We use KZG to commit to each row separately. This way we compute what's called record commitment. And after we've committed to the source record, we sort of change the perspective, how we look at things. You can say flip. And we'll start looking at them column-wise. So we're looking at columns, which are like the first chunks of all the records, the second chunks of all the records, the third chunks of all the records, and so on and so forth. And we apply erasure coding on those columns instead of row-wise. So as you can see in those blue arrows, the commitment and the erasure coding, well, they don't go in opposite directions, but they don't go in the same direction either. They go orthogonal. Once we have applied erasure coding to the record data, one trick that we can do is we apply erasure coding to the commitments themselves. And the magic happens where we can now show that the erasure coding of the data has been done correctly if the commitments that we have just gotten from erasure coding the commitments column are actually the same as if we would have committed to the extended data. I know it sounds confusing. It has took us a long time to click this ourselves, but it works. We kind of have an actual implemented prototype. Wonders of elegant math. So after we have gotten all the erasure coded data, source commitments, and erasure coded commitments, we take all of those commitments and we commit to them again, just so we tie all of these records together in one single entity, which is the archived segment, the product of our archiving process. And once we have committed to the commitments, basically building another layer, we save the segment root. The segment root is going to allow us to prove that each of these records belongs to some segment in history. And the segment roots are stored in the state, and they are included in the next block after archiving. So basically, the commitments to history come back to our chain history and get included in the history again. So it's a wheel that never stops. With this two-step commitment, we can prove that any chunk belongs to any record and that any record belongs to history. The final archived segment is going to consist of 256 pieces, where each piece is, as I've shown, a record, a commitment to that record, and a witness that the record belongs to the segment. This gives us a set of pieces that is now ready to be distributed to farmers. So archiving, as I've just described, is a part of a way more extensive continuous process called history post-processing. I will only be giving a little detail here because, well, you can see this diagram is enormous, but there was nothing I could remove from it. When we have enough history to be archived, that is 100 blocks deep from the tip, well, we archived it as just described on the previous slide. We distribute the resultant pieces to farmers. We add the segment root to the roots table in the state, and we add it back to the history, and so it goes on. When you have time later after this presentation, you could come back and look at this diagram in more detail, but otherwise it's going to take a long time for me to describe it exactly. So next step after the pieces are ready is plotting. Plotting is a process of creating and maintaining plots on disk. The result of plotting is a plot that is consisting of several records, of several sectors. Each sector contains the encoded replica of a uniformly random sample of pieces across all of the history up to that moment where the plot is created. The plotting protocol has been redesigned entirely. So as a result, this is going to be the most technically intensive part of this presentation, if archiving was not intensive enough. So plotting resides on the two core ideas as well, erasure coding, yet again, and memory bandwidth bound encoding. The combination of these two lets us have unique and provable replicas at each farmer that are also hard to fake with computation, hard to compress, and are efficiently verifiable. So let's see how we actually achieve that. And we are achieving that standing using the magic of open source industry and taking ideas of people that have already implemented them and making them better. So the idea we're taking from the paper, Beyond Hellman's time memory trade-offs, that it actually gave roots to future Chia green paper and Chia implementation. And we're using the Chia proof of space, but as a memory bandwidth bound encoding function to mask pieces in our plot. So in short, this proof of space generates a table of permuted outputs of some random functions. I'm not going to go in a lot of detail what it do. You could just treat it as a black box, just as a table of a lot of values. The table depends on two things: a memory requirement parameter that will determine the size of the table and the amount of memory that the farmer has to spend to create it, and seed, which is going to determine the random function and ultimately the values in the table. When you query the table at some index, it's going to output a short proof of space that can be efficiently verified. So for simplicity, you just imagine again that the table is a black box. You ask it for give me a pref at index 5, and it gives you one. We're not going to use it directly to prove that a farmer has a certain amount of space like Chia does. Instead, we're going to use it to prove that the farmer has used the required memory bandwidths for plotting. Let's see how that's done. So a farmer plot can encompass the whole disk or span over multiple disks. It does not have a size limit, but each plot is divided into the same sized sectors. Same for everyone. We're now looking at around 1.3 gigabytes. Each sector is a pseudo-random selection of history pieces, which is around 1,300 pieces. They are uniformly sampled throughout history up to that point where the sector is created. So for example, if the farmer creates a new sector when there was 4,000 pieces, then his 1,300 pieces are going to be a random selection of just those. The farmer has to save the current history size because it will determine the point in the future when the sector will need to be updated with newer pieces, and I'll be describing this mechanism later. After the farmer has collected all of the pieces or downloaded them from the DSN for the sector, they create the encoded replica. The encoded replica will contain only the history data, so the record part of the piece, and the commitment and the witness that are also included in the piece are going to be saved separately, and we'll need them for farming. Each record is encoded separately and sequentially, and everything that I'm going to be talking from now until the end of plotting is going to be with respect to each record separately and sequentially. So for each record, a farmer first derives a unique pseudorandom seed based on a hash of their public key and a piece index and some other public information that is publicly verifiable. Based on that seed, they generate a Chia proof of space table of the size that is required by the protocol. So that size is going to be same for everyone, and it's going to be based on whether it's going to be the ultimate piece size. Given the table, the farmer needs to query it from, sorry, I need to get some water. So creating this table actually prevents farmers from creating the replicas on demand and lets us verify that the farmers have actually spent some work upfront to create their plots so that they are not fake in storage. So after they create the table, they need to derive some starting index for lookup. Can be 0, can be anything. We're still determining that part. And it will also serve as a starting index for the erasure coded data. They query the table as a black box, imagine, for the 32,000 process space values to mask every chunk of the record. So if our record is 32,000 chunks, we need to query the table 32,000 times to get a value for each of the chunks respectively. And once we've done that, we save them and we come back to the record. We interpolate a polynomial over the record, as I've described in the KZG commitment parts. We represent our original record as a polynomial, and we erasure code it by evaluating it on the indices that we've decided to query the table in. And we take those proofs from the table and we just XOR them with our data. So you can see how it's different from Chia, because Chia just generates the table, that's a big one, and saves it on disk. That's it. We actually use it to mask our useful data and to use its perks of being efficiently verifiable and requiring the memory work that we want our farmers to spend. So after we have encoded each chunk by XORing it with Chia, we're basically done encoding. What we do now is we wait until we have encoded all of the pieces, all of the records in the sector, and we spread them into buckets. So you can imagine them as we kind of, again, transpose the perspective that we look at things. So basically, each bucket is going to have a column of chunks. So the first bucket is going to have the first chunks of all of the encodings. The second bucket is going to have the second chunks of all of the encodings, and so on and so forth. Each bucket is going to be then later a potential winning ticket for the lottery. So that's why each bucket has chunks from all of the encodings from the records that we are storing in sector, because it lets us show that the more records farmer is actually storing, the more the chance of winning is. The S buckets are written to disk, and the plot is done. After, well, the sector of their plot is done. And they can start participating in consensus, at least with this one sector. If they have space for more, they can always encode more as much as they can. But at least this sector is done. And so let's say our farmer goes and tries to win a block. Once the farmer is participating in farming or audit, they're trying to solve a puzzle that is based on their plot. The farmer is auditing each sector for a solution and proposes a block if they find a solution. We have designed the audit to be friendly to the SSDs by favoring smaller reads. And concretely, a farmer only reads a 32 kilobyte location per sector, and they only need to read more if they actually win the block. So if they don't, they do just as many small reads as they have sectors. And 32 kilobytes is supposed to be somewhere in the ballpark of the standard SSD page sizes, so it's supposed to be very efficient. But we're going to benchmark that and see maybe we can find a more efficient value. So to participate in the current block puzzle, the farmer awaits the announcement of the global challenge, and they derive an audit index for each of their sectors. So let's say they just have one sector, so we derived from the global challenge some audit index. That audit index is going to be the index of an S bucket that they read from disk. So they read an S bucket from disk at that audit index, and they scan it, the whole column, for one of the chunks that is within the acceptable solution range. And you remember if I said that each bucket contains chunks from all the records. So if farmer is honestly storing all 1,300 records that we asked them to in the sector, they have more winning chances. If they would be, I don't know, lazy or try to fake or save on storage and store less records, then their winning chances are actually less. And that's exactly what we wanted. So suppose they find a winning chunk. In that case, they identify which record it belongs to by the index of position in the bucket, and they read from disk all of the other chunks that belong to this record. So this is the only case that they need to read more from disk when they actually win. So they read all of the encoded chunks of this record, and they compute, again, a Chia proof of space table, which is very fast for one piece, but was difficult for them if they wanted to do the whole plot. So for one piece, it's fast enough. So they make the table, they query the needed process space, and they XOR them back. Well, XOR is a pretty easy operation, and so they are getting the erasure-coded data and the polynomial that expresses that erasure-coded data, that is the erasure-coded data of some history data. Once they have that polynomial, they can compute a KZG witness that the chunk that has won the challenge, that the chunk that they claim uh, is a winning chunk, actually does belong to some record in history. And so it is a valid replica of history. It is not just some random data, some random chunk that they have generated or claiming has won the challenge. So they build a proof. The proof is going to be including more things, which I'm going to show in the next slide. They build a proof of that the replica is a valid one and that their solution is a valid one. They attach it to all of the transactions that they want to include in a block, and they propose a new block. Hooray. To actually prove that they have won, the solution has to include a bunch of things. So it has to include the winning chunk, obviously. It has to include the index of the chunk to be able to actually KZG locate it on the polynomial and verify it. It includes the proof value from the chia table that is showing that the farmer has honestly spent the memory bandwidth to plot this record. And well, it works wonders because you can see that this proof is just 128 bytes. So that's super short. We need to include the record commitment computed at archiving that we have been storing. We need to include the record witness that has also been computed at archiving. And we need to include the KZG witness that our chunk, the winning chunk, belongs to the record that we claim it belongs to. That's a part of history. And then we include some other public information, which is our sector index, the size of history that was when we actually plotted that sector, and our public key. The size of history is needed so that farmers cannot send solutions that are or too far in the future or too far in the past. If they are, if their sector has expired, and the total of all of this is just, well, 346 bytes. We may also include signature and a few other things, but it's like astonishingly concise across the industry, which is going to work great for our scalability, which was the main pressure, one of the main pressures from Jeremiah. And I was like, yay, we can have 1 kilobyte proof. And he was like, no, that's too much. We need to have less. And so we've come down to 346 bytes for now. Let's hope we don't have to add more because Jeremiah is going to be upset if we do. This concludes the consensus. What?
Can I have counting?
We are going to be taking questions a little bit later.
Yeah, sorry.
Yes, so this concludes the consensus part of the presentation, but there are some few more essential things that I need to describe, and we still have some time. So another essential thing that is not exactly part of consensus, but it is at the heart of our proof of useful storage, is the ability, well, to actually extract the records from our useful storage. And extraction is a process of transforming the encoded archived history, well, back into blockchain history by requesting all the needed pieces from farmers and reconstructing back whatever was there. Could have been relayed from another chain or some user file or, well, whatever we want to put on Subspace. In practice, the extraction of archived pieces from cold farmer storage is performed only when the needed piece is missing from the DSN cache. So we aspire to make this a rare event, which is supposed to be happening thanks to hard work from Shamil and others. And so we hope this is a rare event because recovering pieces from farmer plots is going to be much slower because it has to be doing a lot of heavy field operations. So nevertheless, it should work, and when needed, we should guarantee retrievability. So when requested a piece at a specific index in history, the farmer looks at all of the metadata for the sector they have saved, and they see where exactly They need to find this piece in their plot, and they go in that sector and they read all the encoded chunks from all of the buckets that they need to. Same as in farming if they want a solution. So they read all the chunks that are supposed to be part of this record, this piece. They derived a proof of space table again, which is pretty fast for one piece. They get all the needed proofs that they need to decode the record, and they XOR them with, well, after they have obtained all the proofs on this slide, they XOR them with the encoding, and they recover the erasure coded data, which is so far same as in farming. The only step more that they do is that they have to actually recover the source data, which was not necessary during farming. So they interpolate a polynomial over the extended chunks, and they evaluate it back on the source indices, like 0 to 30,000. And they combine back nicely concatenated piece, which is the record data they had just recovered, the record commitment from archiving that is supposed to be correct, proof that this data is correct, and the witness that it actually belongs to history. Packs it nice, sends it back. That's it for instruction. Last thing that I wanted to show with all of this is updating plots. This is something that I have mentioned a few times already. If you recall that when the farmer creates the sector, there's just this many pieces in history at the time that exist. So eventually, the history grows, and that the farmer sector is not storing any new pieces that have been created. So we want to keep the older pieces and newer pieces more or less at the same replication factor. So we had decided it's essential so that the plots are updatable to force farmers to once in a while download also new pieces from the chain, not just the old ones. So when they were plotting the sector for the first time, they are also saving the height of history at that point. And when the history roughly doubles in size, which we can calculate and expect it on our chain growth archived up to that point, they run a check and see when they should update the sector, which is going to be a pseudo-random point somewhere in the near future. When that time comes, they simply just erase the sector, which, if you recall, 1.3 gigabytes, and they replot it again. Since they are forced to resample the pieces in history, this new sector is now also going to contain some percentage of newer pieces that have been created after their selection. So by doing this process of each farmers that have expiring sectors all at the different times, we are balancing the replication factor of older history versus newer history. And the new sector is obviously going to contain entirely new different set of pieces, and is going to give them different chances and different lottery tickets to participate in consensus. And I have wonderfully finished everything I wanted to show exactly on time. I do also have a few more slides for those who are super curious about more caveats and intricacies of these algorithms, which you will be able to find on the slide deck, which I'm going to share again in general for you. And yeah, unless maybe General Jeremiah wants to add something, I think we could go into questions.
No, that was great, Daria. We just need to fly out to Stanford now so you can present it to Dan.
Was this recorded? Oh yeah, I hope so. Well, I also have a lot of these points written down, so should write probably a series of blogs on it, which will complement the Ozgun's blogs on KZG. And so, yeah, I know this has been a lot of dense information, and I have been speaking very fast to try to fit it all. But yeah, if you do have any questions, please go ahead. Yeah, go
No,
ahead,
go ahead.
Jerome.
Thank you for the presentation. It was really nice, and I'm looking forward for the slides to repeat it. But I have several questions. So just to confirm, currently with the new one, minimal plot is 1.3 gigabytes. Is it correct? Okay. Also, on expiration for sector, the whole sector dropped. No piece rewriting as we considered before. Okay.
Yes.
Solution structure. Why total pieces and sector index is 4 bytes?
Sorry, I'm trying to find that slide. Oops.
Maybe I understood it incorrectly, but total pieces and 4 bytes seems
So it's a lot. Yeah, maybe it can
awkward.
be less. So with 2 bytes, you can express what 65,000 total pieces, which is a
Right.
lot. With 4 bytes, you can express. Yeah, I know. What's our expected size of total pieces? We kind of thought 4 bytes would be enough. But thanks for raising that question.
4 billions plus. What are we talking about? This this will be total pieces for the sector or for this plot or for what we're
For
talking about here?
for the history at the time that the sector was created. So Nazar in the comments says that it should be 8 bytes.
Yep,
Yeah.
at the very least.
Okay.
And
Yeah,
yes,
I
the
told you
same
like
the same for
the
sector index
specific
as well. My
numbers.
question is.
Yeah. Well.
Okay, then yes, sector index and total pieces should be increased. And also the last question I have that does sector as a word has its some original metaphor related to geometry, as it had, if I'm not mistaken, in the consensus V1. So why do we present it in this way as part of the circle? Because I could be mistaken, but it could be the same if we just draw it horizontally and switch part of that figure. But for the consensus V1, we had some geometric meaning for that, because we presented our piece index hash addresses in some kind of
Yeah, so in
circle.
consensus we won. Let me explain maybe something what Shamil meant if I understood correctly. So in consensus V1, the pieces that were stored in the sector of plot were not a random selection of history. They were sort of a sector of pieces that are close to the farmer's public key on one side and another. So it was actually kind of, well, a sector in a metaphorical sense from history. I have decided to draw it as a sector just maybe from analogy from disks. Like there's a disk and disk is round and we
So
have
it's
data,
just
but
kind of legacy
it's a
legacy term. We don't
visual.
have that original geometric meaning to that attached.
No, and I don't think even like on SSD is going to be like a sector anymore. But yeah, it's just easier to visualize the way.
Okay, okay, thank you.
Yeah, I have, for those who may have not noticed, put the slide deck in the comments if you want to scroll through it, and in the comments, in the messages of this meeting. For those of you who want to scroll through it and see, maybe you want to ask something. Yeah, go ahead.
Yeah, I was going to ask, what does total pieces actually refer to, and why do we need it? Like, yeah, can you elaborate on that?
So this total pieces is the total pieces at the time that the sector from which this winning solution comes from has been when it was created. So basically, when I was creating the sector, the history was whatever, 12,000 pieces. So this will be the total pieces that I will be including. And this will allow everyone else to verify that my sector has not expired yet, or that I'm not putting some value from the future or something that makes sense. But it's basically to, and it's also used in the derivation of like the pieces that the farmer has to store depend on it, and so on and so forth. So it allows to verify several things, but mostly to, yeah, because when the
Okay, thank
farmer
you.
was creating the sector, they were actually computing. They were selecting pieces from like 0 to whatever 12,000. So they need to prove that their verifiably random selection is verifiable with respect to the history that was there at that moment. But yeah, Jeremiah is suggesting alternative names which we may review. Okay, who else? Rahul.
Hey, so one question, like now we no longer have a VDF kind of thing, right? Instead, we have a memory intensive
Yes,
method, right?
we do not have a VDF in a sense of delay in computation or delay in time, but we do have a memory bound or memory hard or memory bandwidth bound. There are a lot of different namings in different papers, but we basically, the bottleneck that we're trying to induce on a farmer is that they have to spend a certain amount of memory, so they cannot do as many
Yeah.
of those things in parallel because their memory is limited.
So I guess my question is like some farmers can collude to build like a distributed cache or something so that they can build, I mean, they can solve the puzzle more easily now instead of having to compute the solution on the fly, right? So is my understanding correct, or we are not concerned with that?
I'm not sure I understand your question correctly, but so the scanning for solutions happens on the chunks that are encoded after the table was created. So if they wanted to do something on the fly, they would have to create the table for this record, scan one chunk. If it's not winning, throw it away, create the table for another record, scan one chunk. If it's not needed, throw it away. So that doesn't, that's too much work that needs to be done repeatedly after each slot. And if they do it for more records in the time for 1 second for one challenge, they may not actually make it in time to submit a solution, even if they find one, and they will have to do it all over again at every slot. But if that's not what you have been concerned.
Yeah, that kind of answers my question. My concern was like they could cache somehow the solutions in advance so that they can serve it immediately and have an unfair advantage over others. Because now with the VDF, I think you cannot predict the solution until you get there. Right now, that is not the case anymore. You could basically know in advance. I mean, there's no delay component to this anymore, right?
Let me just jump in, Daria. There wasn't really a delay component before Rahul. Even though it was a slot was like a time delay function, we weren't using it in the setting of a PDF. So it was still a throughput bound plotting process, even though technically there was a time delay, like a very, very small time delay for sloth. So it's still the same, basically the same constraints as before. It's just now it's instead of being computationally bound, it's memory bound, or memory bandwidth bound to be more specific. And the analysis is that the memory bandwidth of modern computing architectures that you can actually saturate that pretty easily and still make the plotting process something that you can do in a reasonable amount of time. But it really has nothing to do with the delay.
I see. Okay. I think Nazar also posted an answer on the chat. He said they can't know the person in advance more than C height or something. So I think that is what I was looking for. Thanks. Thank you.
Yeah, I think the current prediction window, this was called to know the challenge in advance, is set at something like 25 minutes, if I am correct.
I guess this comes from the C correlation
Yes.
algorithm. Okay.
And again, if that is too much or not sufficient, we could adjust that following the formal security analysis. This is just what we have, how to say, assumed as would be a good value.
Yeah, and we are planning to upgrade with a proof of time, which will bring that down to a few seconds. But that's unrelated to this. It's a whole different notion of a VDF.
Any more questions? Or if no one has questions, I could go into more sophisticated stuff that I do have, because this is this has been, especially plotting, has been a little bit simplified for the presentation.
I am curious, actually, from the group, if anyone has any feedback on the design, if they see any concerns or any issues. Maybe it's even something that's not necessarily technical, but maybe some sort of concern on the user experience or some maybe sort of second or third order effect of some of this, maybe what y'all's reactions are to this so far.
I'm still trying to digest a lot of the technological side of things. From the community side, I think really just the biggest open question is how to properly, I guess, merge from like the old hard drive way to the new, SSD only way. But that's kind of been an open thing that we've known for a while and have been addressing as we progress. But still kind of trying to digest the technical side of the implications and everything.
Good, Joe.
Yeah, thank you so much, Daria. I thought the presentation was actually really helpful with all the diagrams and all the explanation. It was really helpful. But I do have a question. I'm not sure if I understood it correctly, but when on the extraction slide, you mentioned that while we will be able to guarantee retrievability, but it may be slower. In regard to our go-to-market, like the metaverse, does that influence or affect anything in terms of like our best use cases or customer user experience? And I have a second question. You mentioned that the farmers will have to eventually, once in a while, go through like a phase where they have to erase everything or erase expired sector, and they have to download everything. Sorry. In that process where they have to update their sectors, are they going to feel anything, notice anything? They're not going to be able to earn rewards for that time being, right? So is that something that they're going to be able to notice, or is that just so like minor that they won't even notice anything?
Okay, I think for the first question, what I meant is that the extraction from the farmer plots is quite slow indeed, but it's not going to be our first and main way to get pieces. I know maybe if Shamel or Jeremiah want to jump in and describe that cache process a little bit better.
Yes, I could do add to this that the intended source for pieces would be cache. So we take those pieces into cache first, and then we have cache miss, so we can't get it from the cache. Only then we get to that slow extraction process. So we designed it to be less probable to get this extraction process. At first we will take it from the cache. I hope it makes sense.
So
Yeah, one way to think about that, Yewan, is kind of like on the internet, you have a CDNs, like content delivery networks like Cloudflare, and most of the time the websites aren't delivered directly from the server. And so we've built something similar. Shamil has built something similar. So there's like a hot cache, kind of like IPFS in a way you could think about it. And only if that cache, like the data gets erased or deleted or dropped from that cache, then the actual cache farmers or the other participants on the network will repair that cache by going to get the data from the farmers. So it's kind of a last resort, but it's not like the primary way of retrieving data like it was in version 1 of consensus.
Okay,
On
thank you
that
so much.
point, just on that point, how Shamil or Jeremiah, how long do you think it would take to get like enough storage on the network for that cache to be like used effectively in its theoretical? Like, because right, like LimeWire has to have a certain number of people like caching content on the network before it's like highly effective. Like, how much of that would we need to like bootstrap on our own for that caching system to like be working optimally?
That's a great question, Ebony. We'll have it from day one. It actually is kind of independent of the size of the network or the amount of space pledged, because for the most part, like almost every decentralized storage network like Filecoin, Arweave, storage, they have far more, like 1,000 or 10,000 times more storage than they have space, actually, like useful space that they're storing or like utilization. And so it's probably not going to be an issue.
okay, then for your second question about the updating plots, so the farmers are not going to be updating. We'll assume most of our farmers are going to have more than 1 gigabyte pledged to the network. They will not be updating all of them at the same time. So they will be expiring one by one, well, not sequentially, at some random times in the future. And they will be replotting, yes, each sector that has expired. They will be deleting it and they will be replotting it from scratch. So they will not be able to participate in consensus for that particular sector. But if they have more than one sector, none of them, well, randomly, none of them should expire at the same time. So they will still be able to participate in farming for all the other sectors that they have.
Thank you.
Though we're still figuring out the exact mechanism that this is going to work. Any feedback on the new name from the community and marketing perspective? Dilithium consensus. Our first consensus did not have a name. Well, as far as I remember.
I like it. It fits with the Star Trek theme.
Yeah, I like the AI generated image. It's kind of cool.
Took me like, I don't know, half an hour to get the image that I liked, but I think it's worth it. It's not wasted work time. I hope you like my purple team. I have copied the squares from the all hands presentation, and
Yeah,
I
I
had first
noticed that. I loved it. I was like, nice, Daria. Awesome. It's good.
I first copied like the whole all hands dark team, but then the issue was that the white diagrams were not really nice, the dark team. So I thought the purple one is going to be nicer. Yeah, it was very important step of the work to get the aesthetic satisfaction with the content that I'm delivering.
Okay, Daria. To close out here, I just wanted to give a big shout out to Chen, Dr. Chen Fang, who's on the call right now. Thank you so much for helping us to formalize and all the feedback and all the ideas that helped help build this. It was a really collaborative process, and couldn't have done it without him. So thank you so much, Chen.
Yeah, very welcome. Yeah, it's my great pleasure. And for other team members, right, you know what? Now we are sending this document to other researchers, driving them crazy, come up with attacks, right? Figure out some loopholes. And so far so good. And so far, right, I received many questions and from researchers, and most of them about clarification, nothing about potential attacks, and I will keep you updated.
Yeah,
some of the
ahead,
ideas that they're used here are really intricate. They're not that have not been used anywhere, and they're coming from Chan and Jeremiah, and it's super cool, fresh look at erasure coding has existed since the 50s, the 70s, and we're having a completely fresh look. So that's super cool.
Yeah, and Chen's also written a paper that I would, I don't know, I would encourage you to read it, but it is there if you would like to check it out. It's got a lot of heavy math in it, but there's a formal paper.
Mm-hmm. Yeah, and also meanwhile, right, I'm trying to popularize and our new construction. For example, right, I will go to University of Toronto very soon, right, and try to kind of talk about this new construction. And last Friday, I had a chance to speak with head of research and education at Cardano, and they are also interested in this because data availability, right, is also important for Cardano. Yeah, so meanwhile, so basically, right, on my end, I'm working on two things, right? Number one, with multiple researchers to go deeper about the security analysis. And number two is more about education, right? Reach out to others. Hopefully, right, and they will love our new construction. And on my side, I'm totally, as Daria said, I really love this new construction. It's a combination. It's a team effort. It's a combination of several beautiful ideas. And one thing, right? Maybe I will just point it out one thing. Previously, right? Daria explained that the beauty is for different pieces, right? You need to use different this POS tables, right? Which means that the memory I/O scales with the number of pieces as a farmer, and that's why, right, for malicious farmers, it's hard for them to emulate, right? Because when our lottery is across so many different pieces. This is what we know already, and there is another perspective. Even if, right, two farmers share the same piece, because it's random selection, right? It happens that two farmers are sharing the same piece. You know what? Because they have different farmer IDs and they will use different POS tables. So that's why, right, it makes malicious farmers hard to collude with each other. Even if, right, they have the same pieces, hard for them to kind of reuse the POS table. So this increases security a lot. Yeah, so that's all from my side.
Go ahead.
Would I be wrong to consider slide 6 as sort of one pager on comparative advantages between the new consensus versus the old?
Well, yeah, try to make it so. This again, it's not the exhaustive list, but it's supposed to be the biggest changes. But we can, if we want like a formal one-pager, we can always get one if you need one.
Yeah, I mean, yeah, I think it will be very beneficial, especially for the ambassadors and for those who are very familiar with Consensus V1, and also to enrich our educational database. But no, we can. I don't want to give you any more work. We can start from there, and if I may, I will ask questions to the team on how to make the one pager. Thank you.
Do you want to
Yeah,
say something, Jeremiah? Oh, yeah.
Yeah, I was gonna say, we've recorded this and there's nothing stopping us from sharing this with the ambassadors or with our community. We just have to caveat that this is not, not formally audited, not a secure construction. We're still working on it. But there's nothing proprietary that we're, trying to hide here. And one of the other things that we've also, Jen and I have talked about, is starting to, now that we're having lots of other researchers, I think there's something like 5 other researchers now that are working with us, to move this to our forum, to actually build out a research topic in our forum and start having the discussion there. And so Chen, Fredik, who just spoke, and Justin, who spoke earlier, they actually are the maintainers or sort of the admins for the forum. So and one of their sort of objectives is to try to help get more activity going on the forum. So this could be a great place to start.
Yep.
Yeah,
Exactly.
we have a lot of written for this presentation, for the spec, for our research documents. So if there's anything, I don't know, you think should be posted or somewhere, I'm like eager to give you a lot more material and always help, because we have written a lot, and it would be really good to post it publicly for the fruits of our work and the steps that we've taken in between.
All right, well, great, Daria. Well, if there's nothing else, I know we've all got a lot to do, so we can give you back some time. If any of you would like to dig deeper into some of the technical components, Daria's still got 15 minutes if you would like to stick around. But we really appreciate such a huge turnout, and thank you so much for Daria for doing such a great presentation.
Yeah.
Amazing job, Daria. I'm so proud of all 3 of you, and I love you, Dr. Chen. Thank you for all of your contributions. You're so awesome.
My pleasure. Thank you.
Thank you, everybody.
Thank you. It's
Thank
been
you.
great to be able to finally share in a comprehensive way the work that we've been doing, what's like 6 months. It feels great. Yeah, if anyone wants to stick for more technical questions, I can stick here for the end of the meeting.
Hey, could you go back to that slide where you showed the extensions and the plotting slide, the picture? I just had one question.
Yeah, sorry. I just got the notification that was say that people were dropping, that was covering the button with the slides. This one?
Yeah. So what actually gets stored in the disk is like the actual chunks from the record are not stored, right? It's the evaluation of the polynomial at the indices XORed with the proof of space table is what actually gets stored, correct?
Yes, correct.
Okay, so we don't actually keep the original record chunks in the disk.
So we do not keep the original record chunks in the disk. We keep the erasure coded copy from which the original data chunks are recoverable. And because of the amazing ways that KZG interoperates with polynomial erasure coding, when we store the erasure coded copy, we can still prove that these chunks did actually belong to the actual source data without having to recover the source data. This is like magic. That we don't have to recover the source record to prove that our winning solution is actually correct for some part of history. By storing that in coding. And what's making, well, one of the things that's making the replica unique is because the proof of space table is unique. So if everybody was storing just the records, then their winning solutions would collide. This way they don't. And the erasure coding is actually also needed for the way we treat the Chia table, because in this presentation I have simplified it a little bit. It's not all that, well, butterflies and rainbows. So the actual erasure coding is actually really essential to this construction.
Yeah, so one suggestion I was like, maybe change the polynomial extension to something like polynomial evaluation over the indices or something like that, because this extension is not very clear.
Yeah, I had doubts about the name as well. I know, because I was trying to maybe name it like erasure coding, but it's like not exactly the classical erasure coding that's referred to.
It's not. You are actually evaluating the polynomial over a different set of points, right, and storing it, right? So maybe
in literature it's also called like polynomial oversampling, but that's kind of sounds too machine learning-y. So yeah, we didn't have a good name yet. Well, there another possible name is like parity values, but that's also not really clear. But so yeah, if you do find a better name, we would appreciate. But now we are where we are. Well, if no one has any more questions, maybe we can close this up. Get you 10 minutes back.
thank you.
Thanks, Daria. This was great.
Thanks, Daria.
Thank
This is
you.
well done.
Thank you, everyone, for sticking around.
Thank you,
Listening.
Daya.
Thank you.
Bye, everyone.
Bye.